Good afternoon, everybody. Welcome to the College of Engineering Virtual Brown Bag Series. My name is Gautam Das, and I'm the Associate Dean for Research at the College of Engineering at UTA. And I'll be the host of today's presentation. You know that we have been having this Brown Bag Series most weeks for the fall semester, and we have an exciting presentation today. Our guest speaker for today is Professor Luca Maddalena from the Mechanical and Aerospace Engineering Department at UTA. I'll tell a little bit about Luca in a minute. He is going to talk about the National Hypersonic Testing Facility at UTA. He directs the Aerodynamics Research Center, and this is one of the only university-operated large-scale arc-heated wind tunnel, so we will hear a lot more about it. Just wanted to mention at a higher level that aerodynamics and aerospace research at UTA is very well regarded, and we are one of the big players in Texas and perhaps across the nation. Our funding in aerospace research is comparable to UT Austin, so that's a great news to share. Professor Maddalena is internationally recognized, and we are very happy to have him as a part of the UTA faculty. He is the director of the Aerodynamics Research Center, and a little bit of his background. He is from Italy. He received his laureate degree in aerospace engineering from the Polytechnic University of Milan. His PhD was in aerospace engineering for Virginia Tech, and after his PhD, he also did a postdoctoral scholarship at Caltech, at the Graduate Aeronautical Laboratory of Caltech, and then he came to UTA, where he's gone through tenure and promotion, and he is currently a full professor of aerospace engineering and the director of the Aerodynamics Research Center. He researches in a lot of areas in wind tunnel research. I will leave it to him to describe some of the details. It's a little bit beyond my expertise. He has got significant funding from a variety of federal and DoD sources. The list is a long list: NASA, Office of Naval Research, Air Force Research Laboratory, DARPA, and so on and so forth. So he's got a lot of funding for us. He is a fellow of the Royal Aeronautical Society and associate fellow of the American Institute of Aeronautics and Aeronautics and AIAA, Aeronautics and Astronautics. He presently serves as deputy director of aircraft technologies within the AIAA Aircraft Technology Integration and Operations Group. He also has served as chair of the AIAA's Hypersonic Technologies and Aerospace Plane Technical Committee from 2017 to 2019. So he is very well connected with a variety of professional societies in his field of research. And it gives me great pleasure to turn it over to him to talk about his research to us. Professor Maddalena.
Thank you, Dr. Das, for this fantastic introduction, and thank you to the attendees for taking time to look at this presentation. Just a little reminder, so this is a non-technical presentation, so not strictly technical, but nevertheless I wanted to provide the audience an idea of what we do, the Aerodynamics Research Center, and particularly about this jewel that is the new facility we'll try to understand a little better, which is the only one in the academic community, and there is a reason for that, and only among a handful in the entire country, so we will see. So please stay with me. I will try to use some loose words, not to be too technical, but the idea again is to present what we do, the excitement and the capabilities of our system. Now, before talking strictly about the new wind tunnel, this is a picture of the Aerodynamics Research Center. You see the view from the outside building. Where are we located? We are located at the southeast corner of UTA campus, and is pretty much one block south of the College Park Center. So this is the geographical location. The center has been established in 1986, so we are now about 34 years. So we are going to celebrate the 35th very soon. And as Dr. Das mentioned, this is well recognized at the national level, but also at the international level. And of course, this is not just because of me. I'm only 10 years part of that, and a couple of years now I have the privilege to be the director of the center, but because of the work done by my colleagues, and let me mention them. Professor Don Wilson, that is the founding member, so that's the one that cut the ribbon in 1986, and Professor Frank Liu, that is the former director of the ARC. And recently we have a new professor that joined our group, bringing in computational capabilities expertise, and is Professor Li Wei Zhang, and I'm sure she will do very well in maintaining the high standards of the tradition of our center. Just to give you an idea, we have a large series of facilities. One of the things that attracted me to come at ARC UTA when I was at Caltech, I had to say I didn't know much about UTA, but when I saw that open position and I saw this picture, because it was posted in the ARC website, I say, oh, wow, I never see a unique collection of facilities in one single place. And in fact, Caltech didn't have all of this, Virginia Tech didn't have all of this. And so, and I understood, being an experimentalist, that would have been a fantastic ground to develop a career. And I had to say, because of this facility, because of the visions of people before me, because of the statue and the high bar that the people in that center were setting, this has been fantastic. And I was able to really progress in my career, probably in ways that I would have been able to if I was joining another university. And so this is something that I really believe in. And now it's my duty to carry on and further expand the reputation and capabilities of our center. As you can see here, we have various pipes, blue pipes, right? UTA blue. This one is a transonic tunnel. Transonic tunnel is capable to get Mach numbers between 0.5 and 1.2, has been widely used for problems where you have transonic flow, like blades for helicopters, and we actually supported the F-35 programs here, particularly when you're flying the transonic regime. The central tunnel is supersonic tunnel, so we can go up to Mach 4. We do a lot of work here in supersonic mixing, fundamental mixing, which is one of the challenges for scramjet engines development. And I'm very proud of this one because one of the first grants that I ever got here was for fundamental mixing, and there was only one award nationally given by NASA Langley, and UTA-ARC was the only recipient among the amazing pool of applicants and participants. So that was the first big proud moment here. The next pipe, and the last one here, is hypersonic shock tunnel, and we can go up to Mach 16. You see here the Mach number capability. Basically, we go from very low subsonic speed, virtually Mach 0 to Mach 16. In the other picture is another room. Is the ArcJet facility, the original one. The original one was actually donated by ADC, and it was brought in by Professor Wilson. When I joined UTA 10 years ago, actually that room and no facility was totally dismantled. And because of an interesting scenario of somebody calling me as soon as I became professor and say, hey, do you know that there is a major heat shield thermal protection system company? And actually, they asked me, where do you live? And I say, I live in Canada. I say, who knows, right? Some people from other states where Canada is. And he said, well, you know that one major company in thermal protection systems is there, heat shields. And I said, no, I didn't know. And I said, well, we had the possibility to bring back an ArcJet facility. And so I started to connect with this company that they were working with Lockheed to develop actually a very advanced vehicle, the Falcon program. And they say, well, if you can do it. So long story short, we rebuilt this facility, the original one, and we started to do some work with them to prove to the community that actually we could do it. So that was a great experience. And then we were actually at the beginning of the early stages of this hypersonic race. Now, from that point to now we are at the topical point of this hypersonic race. At that time, the urgency was not there, but somehow it was prophetic that we started with that because we had an inherent advantage compared to other institutions. Just to give you an idea, so what is hypersonics? Because we will talk about that. Well, when we are flying generally above Mach 5 and above, even if the separation is not a net 1, and to give you an idea, Mach 5 is 3,800 miles per second, so you can go higher than that. Our re-entry space shuttle at Mach 25, 17,000 miles per second. What it means is when you are moving that fast, if you are in the reference frame of your capsule, you see the wind coming to you with the same velocity. Well, if you take that square of that velocity and divide it by 2, you get an idea of the energy. Now, in your reference system, that energy slows down, that flow has to slow down because it's going to stick to your surface. And so that energy is converted to heat. Now, that's a major problem. And as we see major efforts going on globally, primary reactor, us, China, Russia, 2 types of vehicles. We have air-breathing power vehicles, so they are actually getting in the oxygen from the atmosphere for their propulsion system. We have also tactical boost glide vehicles, so you are using a rocket to push them at the limit of the atmosphere, and then they are actually gliding down without any propulsion system to reach their target. In any event, they are going so fast that one major problem is for all of them, the heating. The thermal heating. So just to give you an idea, in many cases, we are exceeding the melting temperature of known materials. And so we need to be creative on how we are actually going to be able to do the thermal management. And since the system is finite, even an active cooling system has to be carefully conceived because you don't have much space, much mass to play with any thermal mass or any ability to absorb that much of that heat. So there are other applications of hypersonics. Hypersonic is not only military, even if now that's the major driver. There will be opportunity for commercial transport at hypersonic speeds. But there is another side, the space exploration component. You see these heat shields. I'm mentioning here the MSL from NASA. So you are entering a planetary entry, like in this case. You are having hypersonic velocities. In Mars, particularly, we have the atmosphere is mostly composed by CO2, so carbon dioxide, and we actually cannot use CO2 in our facility to simulate the re-entry conditions. So having the opportunity to reproduce the heating level that is formed here for the duration of the flight and changing the gases, then allow us to consider space problem related to entry or re-entry, atmospheric entry or re-entry, or problems related to DoD. Now, one of the major points when we were developing this capability, and actually this chart was very liked by various program managers, they always ask me a copy of this. So when we were trying to build a case to develop this facility, we started to look at all the facilities around the world. As you can see, the first take is that UTA-ARC is the only university-operated facility. They are all governments, pretty much. Private Boeing LCAT facility. One comment I want to make here is that NASA Johnson at that time was in, but then was dismantled before the hypersonic race. So that's another thing. So in Texas, we are the only one, and the only one in the country. And you see there is only an handful here in the United States. Then you see Europe. I have not reported facilities in countries like Russia and China, but just to give you an idea what was the business case here. If you see the JAXA, which is the Japanese Space Agency, the JAXA facility, the power is 750 kilowatts. What we have at UTA is 1.6 megawatts. So it's much more power than the national facility of Japan. To give you an idea, how much is that 1.6 megawatts? Well, as a ballpark, you can power 900 homes with that power, right? So this is the amount of power that is needed for this, and I will explain why. So this was a major point to develop this facility here. Now, as I mentioned, as we started to rebuild the old facility, we started to work with companies, local companies, that they were actually developing advanced thermal protection system. As you can see here, I got permission to publish some of these pictures, and here I cannot really disclose what is the temperature on top of this specimen. But how does it work? Let's go with the facility first. You see these big cables here. So the idea is you are passing flow, the most simple concept to visualize how it works. You're passing flow through two electrodes, right? You have the anode, you have the cathode. You are applying a voltage. There is a current that establishes, right? And we are actually applying 2000 volts and 800 amps. If you do 800 times 2000, you get 1.6 megawatts, right? That's a simple calculation. But basically, we are heating up the flow with the electrical energy, passing an arc between a cathode and an anode. After that, we are getting this high energy flow, very hot, and high pressure flow through a nozzle. It expands, and then we put our specimens here. You will see, and I have other images to see. So you see in this case, the flow is coming from left to right. We are putting some specimens there. So among this one, there are this one. We call it carbon-carbon SiC. SiC stands for silicon carbide. So there is a carbon-carbon substrate, the way you make your vehicle, and there are coatings because the temperature are extreme. I cannot disclose the temperature here because this was program under ITAR, but it's generally known that you are interested in temperature above 3000 Fahrenheit for a long time. And that's the complexity on generating these things. Typical results are this one, and they are very complex. So we had the target temperatures that I cannot disclose, but they are above 3000 Fahrenheit. And the silicon carbide is a coating that is made to further protect the thermal protection system. And to give you an idea, the silicon carbide is around 5000 Fahrenheit when it melts. Okay. Now you see here, and I will remind later, that at some point we were washing out this silicon carbide. It forms like glass when it gets heated to that temperature and is exposing the substrate. When you are exposing this one, then very quickly you will go through this material and your thermal protection system will fail, so your vehicle will fail. Now, what I want to mention here, and you see various scenarios when we insert specimens and we do infrared analysis on this. One of the important components to understand is that when we are heating up air at those temperatures, air is not air as we know it anymore. Oxygen molecules break down, those are the first, and they create atomic oxygen. And then nitrogen molecules also break down and create atomic nitrogen. So you have a soup where you have oxygen, the atomic level, oxygen in the molecular level, nitrogen at the molecular level, at the atomic level, NO, nitric oxide, which is something that we need to be careful when we do our experiments because it's toxic, but we have all the provisions for that. And so, and on top of that, the chemistry and thermodynamics sometimes are slower than the flow. What does it mean? That generally when we think about chemistry, you have some reactions, and if I have a certain pressure and temperature, I know the composition of air. Because of the fast speed, we are talking about several miles per second. The chemistry is catching up. And so in every point, we call that non-equilibrium flow. It's not the composition that we will have on a certain pressure and temperature, or was the composition before that's still evolving over the surface of the vehicle. So it's very complex. One of the key points that I want to make without entering too many details is that it takes 10 years to qualify a thermal protection system, which is a major problem. And various programs, including DARPA, they were trying to reduce this time. One of the reasons for this long time to develop thermal protection systems for space exploration or for military application is because the flows that are produced in these facilities have high uncertainty, 25%. So sometimes you really don't know what you're looking at, where you really have the nominal conditions, or you are 25% more, 25% less, it creates a lot of uncertainty, we say. And this is a major issue. Well, as you can imagine, in other tunnels, if you have a 0.1%, 1% uncertainty, you're there, right? 25% uncertainty is the standard for this facility. And that was another reason for us to invest on it, because as you have more uncertainties, you have more room for improvement. Now, the uncertainty is due primarily to the fact that you cannot use conventional measurement system, intrusive measurement system, to go and measure a plasma flow that is so hot. How hot is that? Well, when we are here, when it's exactly where we are putting the electrical arc in contact with the air, we are actually reaching temperature that are at or superior the surface temperature of the sun. And the surface temperature of the sun being 5,000 Kelvin. So we are talking about extremely high temperature. So we are talking about 8,000, 9,000 Fahrenheit. We have those temperatures. So you can imagine that we need to have a lot of cooling, a lot of systems in place to sustain that. You are producing temperatures higher than the surface of the sun. This is the level of that. So this is one example, particularly for the Office of Naval Research, that is our primary sponsor. You see their application, they need to have a system that they can go very fast, but starting from a ship. This is one actually run that we have done in the old facility. Very interesting project, this one, when we conceive a system that has active transpiration cooling. You see that we have here, this cone is actually transpirating some air, and is mounted in a mounted that is built of stainless steel and a very strong zirconia paste, which is the strongest cement that we know to do that. As you can see, the zirconia goes away, the stainless steel melts like nothing, and this one survives. And that was a very nice thing we published, but it's a very interesting area. So we are the only one able to do that. Why? Other university, other facilities can produce very hot flow, but only for a few milliseconds. In this case, we can sustain it for the order of minutes. Now you notice the similarity of this geometry with what you see in this picture here. So particularly when you have a pointed system, the heat flux and the conditions are actually very high. So this was a success on our side, and that's what you can do. You can explore novel techniques. Now, so on the light of that success and the work we had done before, I was approached in 2014 by DARPA and ONR to ask if we can actually improve the capability of our facility. It was major redesign. So this is actually the final drawing minus many other components of a massive new facility. We have retained this part. This is the only part we have retained. We have a test chamber that we can go down up to 0.1 millibars or 0.0014 psi. So very high altitude to simulate conditions of very high altitude. Then the hypersonic flow goes down this tube, which called Hypersonic Diffuser. Now, believe it or not, when people come and visit, they see this tube and they think that is the simplest component of this facility. You go from point A and you take the flow to point B. Well, this is not. The hypersonic diffuser is one of the most complex things. We need to slow down the hypersonic flow to subsonic there. And there are a lot of shocks inside here. And so we have a lot of thermal management issues. Every single component here has to be cooled down properly. We have non-equilibrium flow. So just to give you an idea, over the years, it took more than 5,000 hours of simulation to get this right. After this one, the flow is subsonic. It cools down through a heat exchanger when we are passing water, 300 gallons per minute, 300 psi. This water has also to be cooled with a secondary heat exchanger, and then it's cooled down with a heat rejection system again. And we have a vacuum system with several pumps that they are able to get all the flow. Just to give you an idea of the complexity of this, and there is no book that gives you the formula to design an hypersonic diffuser. So this is one of the complexity, and I had to thank here Professor Oster at University of Missouri that has done simulation for us to support this work. Long story short, if this somehow doesn't work as supposed, slowing it down in a certain way, the number of pumps here will go from 6 to 20 very easily when each pump is $60,000. So there are major implications to that. This is a little story. This is the heat exchanger. So we contacted 50 companies in the United States. There was only one that they decided to be able to take on this work. Why? Because the entry temperature at the heat exchanger was 5,000 Fahrenheit, and we wanted to get down to room temperature in the space of 1 yard or 2, right? So very challenging scenario, very complex system, and that's why it takes years to develop. Now, in terms of capabilities, and this gets a little bit too technical, but this was UTA capability before, this little red area. And now with the new system, we are actually expanding on this, and we see that we are actually overlapping with major national facilities, ADC, NASA Ames, and this is, on the other side, is a performance map comparing with other international facilities. Some pictures here, they show you the tremendous amount of work to design every single piece. One element of pride for us at ERC is that we didn't outsource anything of this. Every single component has been designed, thought, and conceived here. So many simulation, this is just the nozzle, it's this part here. And you need to do the aerodynamics, the aerothermodynamics, and then you need to do the cooling. And you see the cooling analysis here. If you don't cool it right, everything will go down pretty quickly. So we have worked a lot, as I mentioned, 5,000 hours simulation, then a procurement effort to get bids out, getting contractor working, building, installing. So very complex work, but all done at UTA. Now, the first run was done in June 10, 2019, and the inauguration was June 18. So I had many colleagues at the time saying, what are you doing? Are you melting it down 1 week before? We invited members of industry, the governments. We had a large amount of participants celebrating the opening of this national facility. And we took a risk, actually trying for the first time to turn on plasma in this facility. As you can see, we were fortunate enough that it went well, and I want to here kind of make a remark. When I joined as a young assistant professor, one of the presentations that yearly we do to see how we do at the ERC is review how we are doing what we want to do. And Professor Lu, that was the director at the time, he mentioned in one slide, he said, the ERC is not a museum. And it's not a museum. So we didn't want to keep that facility and showing it nice, all assembled, all shiny, because 1 week later we had all these people. A lot of people advised me to wait for the first test after the inauguration. We go and we think about being maverick. We don't want it to be a museum. We want to use it. So the June 10, it was almost midnight, as you can see here, and the group of people that was there turning it on successfully for the very first time, which was beyond any expectation that it worked for the first shot. Now, what I wanna, since we have a couple of minutes more, I wanted to bring you in a little bit on a few charts that I presented during the inauguration day to all our attendees, that basically they go over the entire process and give you the idea of the effort to get a facility like that going up. So I let this video going. It starts from the successful test. And generally we have a little sound on the background, but I know it doesn't work on Teams, so I will narrate. So this is a tribute to all the people that work. This is Dr. Stefano Gulli, now is in charge of a lot of important projects at Blue Origin. This is one of the early designs that our students have done for the nozzle. So we get up to Mach 6. As you can see, the level of details from the mechanical point of view, from the aerodynamics point of view, from the electrical point of view, from the thermal point of view. And many meetings, all these people now are enjoying rewarding careers. This is an example of a simulation where we had to actually study the cooling. So we need to first see what is the thermal load, then the cooling. And this is so-called the throat of the nozzle, so the smallest section, and that's where the melting will occur first. Then at the assembly level, you see the water is moving inside the pipes, and it goes inside and making sure that each single component has the right amount of water with the right pressure, because otherwise you can have boiling, right? This was one of the early design. When we proposed it to the sponsor, we worked hard to come up with an idea that was credible. So this was the original design. Part of our original proposal was actually this movie. And of course, a lot of calculation, but it takes a lot to build up a case, to build a facility that has all these risks associated with the project of this caliber. So we had to do a lot of background work. Now, this is the idea to show how it was before. We dismantled that part. The only component we kept was the heater. And then suddenly we had to build new system, fabricated, put them together. We have more than 150 sensors that control the facility. And as you can see, and we had to build a new building, but it's a major undertaking. Right, so you can see that not only internal structures, at the external part, we have to build new buildings, and then components that extends to other parts of the Aerodynamics Research Center. This was to show how we went through the production. So this is 2017. We had contractors in Georgia, we had contractors in Indiana, we had contractors in Texas, and it was also thought to make sure that we, not one single contractor had all the entire drawings of a facility of this type. And stringent condition, we had to build a condition for which we are saying you need to keep vacuum at 0.1 millibars for 24 hours. And you see these major openings, these big doors, this is a heat exchanger. So you really start with the pipes. I sent my students there to make sure and testing system before they were delivered. In this case, you see the arrival of the heat exchangers, 17 students reviewing what we are doing and making drawings. Professor Luca coming and inspecting what was going on. Here in Mr. Carter, the ARC lab manager, checking things. Some of our contractors, they send us cakes, so we had also jovial moments. And then starting construction, so new building, from breaking the ground to pouring concrete, and then building up the system to host the entire new facility. And all of this, again, I repeat, with a group of college students and our own graduate students and our own postdoc grown inside. So tremendous pride for us to be able to say that it was all intellectually developed at UTA. And of course, many details, right? Then you need to make sure all the systems are connected together, all the system integrations, considering all the variables, perfect installation. And this was the installation of the Hypersonic Diffuser, getting back into the room, cutting the room, getting this out. And we had, I have to say, all the people that you see in this picture really contributed. We couldn't ask for a better group of people to be there. But there was a day and night endeavor to make sure all of this was actually working and working properly. Now you see here various elements where we are actually putting pumps together, the complexity of the cooling system. As you can see the scale, you see the people, you see the dimensions in the side. The funding director of the ERC, again, come in and check. You see the minutia of calibrating all the components, the installation of the nozzle in the room. One picture here, a major accomplishment in terms of installation, but that was far from being done. And as you see, the room is populating with new systems and some jovial moments where people are proud and taking some pictures for them. Now, two people here that they contributed. One now is a research engineer, Dr. Graham at NASA Langley, and the other one, Dr. Gulli, again at Blue Origin. Mickey Mouse came and checked and said the facility was good, so we proceeded. And then you see, as we develop the complexity of the system. This is to show that this is the last rejection component of the heat in the chain, and then wiring. We have at least 2 miles of wires and 150 sensors that they have to talk together. And as you can see, we see now more wires. We see outstanding people. Now, this gentleman first is ADC, where they do ArcJet, and they actually grab it because he had experience on that. And this was one of the final picture before the inauguration. So this was just to show you something. Now, 1 year later, where are we? And this I'm about to conclude. So I'm really pleased. Well, you can see from here that now the level of sophistication has gone up. The Navy has provided us a very advanced system. This is a femtosecond laser system. That system, per se, is worth about $1 million. And this system was so new that some people thought that you may not be able to get any measurements because of the emission of the plasma interfering with whatever you read with your cameras. But long story short, last 2 weeks, with our Princeton collaborators and the supplier of the laser, we have achieved 2 major breakthroughs. So we were able to prove that 2 techniques that never tested before in ArcJet flows were successful. And one was proved on 3 in the night with this group, not sleeping much. And the other one was 10 in the morning, couple of days later. What are these? One is called femtosecond TALIF. The femtosecond laser is a laser that has, when you tell a millisecond is 0.001 second, right? Or 3 zeros and then the 1. A femtosecond is 15 zeros. And so very, very fast. We are able to measure composition and velocity of the flow and turbulence, which impacts also the thermal protection system. So we apply 2 techniques. One is femtosecond TALIF, and it's called 2-photon absorption laser-induced fluorescence. The other one is FLEET, femtosecond laser electronic excitation tagging. Long story short, through 2 breakthroughs, you see we had to do calibration here, so shooting the laser in the plasma flow, being able to see the signal. Going back here, what we've done, for example, to measure velocity, we shoot this laser, we split the nitrogen molecule, and when they recombine, they give us a signal, we are able to find velocity and turbulence. The point that I want to make here is this one. There was a major accomplishment to design this facility, to have it successfully working. 1 year later, we got 2 major world-class breakthroughs happening in 1 week. So this is the way we want to continue, and as you can see, the instrumentation and the capability are increasing, so this becomes really a national asset. Now, what is the secret of the ERC? And that's the last picture that I want to show you. So the secret of the ERC is selecting a group of dedicated people. These are always very special people, very competent. All of the students and the postdocs here, they have a tremendous CV in terms of quality of their publication. And you can imagine they are the one that make all this possible. So we have invested in quality, and these are our own people. These are UTA people, and this is paying off. So this is their major secret, the capability that these people are bringing in. And this one concludes my talk. So thank you, and I hope I was able to give you a little bit of an idea of what we do, even if it was not deeply technical.
Thank you. Thank you, Dr. Maddalena, for a fascinating presentation. So to the audience, if you have any questions for Professor Maddalena, there is a chat window, and you can type in your questions there, and I will read them out to the professor. So please feel free to go ahead and ask your questions. Luca, I actually have a couple of very, very basic questions because it's a very fascinating topic, and I'm not an expert here, so I'm just curious to know some of the basics. So wind tunnel technology has been going for, I guess, decades, right? Many decades, ever since the first aircraft, I guess, went into existence. So what has been the inflection points? I mean, what was the earliest technology? Then what happened? Is it from subsonic to supersonic to hypersonic? Are those main inflection points where the technology had to be changed for the wind tunnels, not for the aircrafts?
Right. So I would say that actually the wind tunnel technology, the wind tunnel functioning per se has not changed, right? The V2, right, rockets that were tested in supersonic tunnels.
Right.
So the inflection point, what you refer, is actually the ability to have advanced instrumentation to measure things and understand things. So this is something very recent. When I was myself a graduate student at Virginia Tech, I could not have done what today my students are doing in terms of measuring the velocity, the turbulence, understanding complex systems. Otherwise, you cannot make more advancements. So it's very critical, the laser diagnostic. The tunnel technology per se has not changed. But what we can extract out of a wind tunnel, it's the critical part right now. And that's why this instrumentation is so critical, because without it, you will not be able to advance.
Okay, thank you. I can see a few questions and comments from the audience, so let me read one of them out. This is from somebody. Hello, Dr. Maddalena. This is Aaron Brown, formerly with the local supplier you mentioned, and now with Lockheed Martin in Grand Prairie. Thank you for the update on your new facility.
Oh, well, can I make a comment? So
please.
Aaron Brown was among the first earliest supporter of our project. So I want to thank you, Aaron, and congratulations for moving into a new position. I was aware of that and looking forward for you to visiting, and thank you at that time to take the gamble to start and investing on us when we were at the early stage. I really appreciate that.
Okay. All right, moving on. There is a question from Chris. Thank you for the presentation. Are there opportunities for undergrad students to get involved in this program?
We say always. So we are always looking for people, the good people, to come in. And the distinction I always say to students, there is a coolness component, right? It's there. But because of that, a lot of undergraduates want to participate. And so you do well on your courses, you do well on what you have to do. And when I say that, I'm not saying you need to have a 4.0 GPA. It's a combination of dedication, knowledge, but you need to do well. Do well in your courses. That's the first proof that you are dedicated and you wanted to succeed. And then the door of our centers are open. Matter of fact, many of our successful story that they are now PhD in government labs, they started as undergraduate and they were their sophomore year. So yes, that's what we do.
Okay. Luca, I want to ask you some more questions when I get a chance. I was trying to understand if there is a clear definition of hypersonics, because it's so much in the news in recent years. So I looked it up like any curious person would, and I found that it's considered to be, definitions of objects that go at the speed of Mach 5 or beyond, maybe 5 to 15, that kind of a range. But that kind of speeds has been there for a long time, right? I mean, intercontinental ballistic missiles, re-entry spacecrafts. So why this new interest? Is it because the interest is how you can control these objects at that speed, or is it that new materials are needed, or what?
So that's a good point, right? Hypersonic is not new.
Okay.
So this is actually a very nice question. Now, going back to the Mach 5, there is no specific Mach number that defines hypersonic. If I can say something that will appear very strange, our facility is designed for Mach 6. And some people ask me, why Mach 6 and not Mach 10 or more? Well, our Mach 6 is equivalent to Mach 12, because the energy of the flow is equivalent to something else. So at some point in hypersonic, the Mach number loses its importance, is the energy of the flow. And we call it hypersonic when certain things happen. There is no mathematical change in the equations of the flow, like from subsonic to supersonic. There is a major change in the equations, and they behave different. From Mach 4.9 and 5, there is no change. It's when certain phenomenon comes in, we have shock layers, we have a lot of phenomena, we have real gas effects. So it's really when certain phenomena occur, and it could be a lower Mach number, a higher Mach number, depending on the condition. Now, the question is why hypersonic is different now? Well, what is different is that if you look at the intercontinental ballistic missile, they are ballistic, right? The idea of ballistic is that that's one of the problems of today. So you have a parabolic trajectory, right? You cannot deviate. And so somebody that see that you are shooting something like that, they can calculate the end point and with having a lot of margins, right? The idea now is to use glide vehicles. So you go up, and when you come down, you want to maneuver. So you are basically you're shifting the paradigm on the defense system. And that's a big problem, right? Some people in the defense industry, they call it an existential threat. You cannot predict where that goes. Doing these maneuvers, so the profile of the mission change brings in a lot of other problems that they were not part of that. If I have an air breathing system that has to do half an hour reaching any point, right, or the other side of the world, it has to sustain the heating for longer time. Right? A capsule coming down is only a few minutes. If you want to extend that period because you're flying straight and you want to reach the other side of the world, then you have thermal loads that are different. So the mission profile is different, and that opens up ginormous amount of problems, because you can get a system working for a few minutes, not necessarily you can get it working for half an hour or more. And so, or then the concept of reusable system. So it's the mission requirements bringing in new issues that they were not solved before, because they didn't have to.
I see. Okay. So, but I just want to press on a little bit on this. I mean, at Mach 5 or Mach 10, how much time does it take to get from any point on the Earth to any other point?
So they were saying they want to go in 2 hours from New York to London, right? And then, of course, how faster you go, you technically in 30 minutes you can reach the other side of the world. But again, that requires brings in a lot of complications, right? So if you think about a capsule coming down, the heat shield consumes, right, as you're coming down, and that's why you see it. And so you can design it for, say, okay, a few minutes, and I know. If you have a long mission, then you cannot play the same thing. You need to think about reusable scenario. Your control system, they are affected too, right? So one thing is coming down with a shape that looks like the classic capsule. One thing is to fly with something that has to be controllable. And so those surfaces have to be preserved. And so that's the biggest complication on the thermal protection side. And then there are other issues related to propulsion, but that's coming next.
I see. And what about extraterrestrial research? I mean, does your facility look at, I mean, you mentioned a little bit about Martian entry and all that, but
Yep.
I mean, do you do any active work in that space?
Not yet, because primary sponsor is DoD. However, we talk with space-related companies, right? We have former students that they are there now. And so we have the possibility on paper, right? We have to test it, but on paper, we can actually feed our system with carbon dioxide and really simulate the condition of hypersonic reentry in Mars. So on paper, yes, we need to try it, but conceptually, yes, we can do it.
I see. Okay. Well, Dr. Maddalena, unless there are any more questions from the audience, I would like to thank you again.
Excuse me just a second, Gautam. I do have one more. I'm just about to push it through here. Just a second.
Okay.
Should show up right now.
Oh, yeah. That's right. Yeah. Okay, so this is a question from the audience. Tim Fennell is the questioner.
Yes.
Hi, Luca. This is Tim Fennell with the Lockheed Martin high-speed wind tunnel. Is your ArcJet facility available for industry to come in and run tests, or are you strictly performing research for the university?
No, we are open, right? As you remember, you came for a tour not too long ago. Thank you for that. No, we are open. We are exploring now the envelope. As you see, the idea was to fully characterize this facility so the customer know exactly the condition we are testing in. So we are in that phase, but yeah, we are open. And what we want to do is a balance, right? Also, as you can imagine, with a lot of other government agencies, they want our support. So we will try to build a balance between work that, of course, our students will not be able to publish and do anything, right? And facility like this requires permanent staff. If you want to think about it, it takes 5 to 6 people to run something like this, and you do one run a day. But we are open, particularly for screening tests, for early stages explorations, absolutely.
Great.
And would somebody in industry just contact you at the ARC to set something up?
We are in contact with many people, yes. And I think one of the things we will want to try to wait at the beginning to make sure we understand the conditions, because you need to know what condition you are testing, right? So as you can see with these results, we cannot just say, okay, these are the expected conditions from our computer simulation. We are sticking in probes now and exploring the envelope, right, that we designed for. And as we know, generally, there are some discrepancy in all the facilities. So we wanted to be cautious at the beginning and use these current projects. And we have also a DOE, a Department of Energy project now, again, to study the effects of the background radiation. So for now, we have 3 concurrent projects. There is a DURIP, there is an ONR, and there is a DOE. But the idea is to support our community. And what I'm trying to push is to expand the critical mass also in terms of the human resources that we have. And I think with the new Hypersonic consortium that is coming out, there will be the opportunity to further expand and then better serve also the industry component. I'm very confident on that. And of course, industry support to get the decision makers to understand this, it's also important. So thank you for all the Lockheed Martin people connected today. I really appreciate it.
Thank you. Luca, actually, I have one last question. I'm very fascinated by this general area. So how critical are simulations vis-a-vis actual experiments in doing some of the research that is going on in this kind of space? Do you envision a future where the wind tunnel will become obsolete and everything will be done through computers?
Of course, as a good experimentalist, I have to say no, right? But so just to say, this was a question that, if you look back, was asked many, many years ago. And what happens, particularly with these new flows, is that our codes, they are not all verified and tested for all these chemical reactions for what we call non-equilibrium flow, surface chemistry interaction, right? So there is a lot of work to do, and I want to mention that very recently we have this partnership with ANSYS too, right? Because they want to develop their systems, and we are actually able to provide this. So what I see that Dr. Zhang that just joined us as a treasure to get this data to develop new models and new capabilities. Otherwise, you will not be able to do. So all this work, particularly the fancy laser diagnostics that generally is beyond what industry will expect for a test, calorimeters and other standard measure. But what we see here will allow people developing codes, and then industry will use those codes. So codes right now are not sufficiently mature for these applications, and that's just the state of the art. And that's why it's good, because we can contribute both on the scientific aspects and the test and evaluation aspects, and again supporting the community. And it's not just a major prime contractor, right, like Lockheed in this case, right? but we are supporting also a variety of small businesses that they are entering the hypersonic arena, and for them it's much more accessible to come to us. Right.
All right, thank you very much. And I think, unless there are any last minute questions from the audience.
None that I see.
Okay, all right. Dr. Maddalena, thank you so much for such a fascinating discussion and for telling us about your facility and the kind of research that your group is doing. We're very happy that you could join us today. So everybody, this is the end of today's presentation. Please be sure to tune in every week. We're going to continue this for the foreseeable future. Thanks, everybody. Goodbye.
Thank you for having me. Thank you.